Hi, I am Emir Demirel, PhD candidate from Queen Mary, University of London. I'm doing my research within MIP Frontiers project, which is funded by Mary Skłodowska-Curie Actions within EU's Horizon 2020 program. In this video, I will be presenting the low memory requiring solution for the audio to lyrics alignment task that we have developed recently together with Professor Simon Dixon from Queen Mary University of London and Center for Digital Music, and Professor Sven Ahlbäck, who is the CEO of the Emir Music Research AB. In this talk, I will first go through the basics of lyrics alignment, then briefly explain the key points of our system design. Then I will show the evaluation results of our system's performance on a public dataset. I will conclude my talk with a short video demonstration. Audio to lyrics alignment is the procedure which aims to match audio frames with their corresponding phonemes and words given their song lyrics. In the image, in the slide, you can see the horizontal red lines, which indicate the word regions that are detected and aligned by a lyrics transcriber. The gray zones with different colors, separated by vertical lines, indicate phoneme regions. When we automatically retrieve such information, the word and phoneme timings, from singing voice signals, we can use them for a number of applications within music information research. One of the first things that come into our minds is the karaoke applications, where you can already find a number of examples within the music industry. Such automatic tools, as long as they're accurate enough, can be used for audio and video captioning and editing. And furthermore, similar to speech recognition research, this lyrics alignment can be used for generating new data for various other tasks, such as lyrics transcription. Moreover, the phoneme segmentation can as well be exploited for song note segmentation and eventually for music transcription. Once we retrieve lyrics timing information and also the lyrics information per se, we can utilize them for a number of other MIR tasks in the context of lyrics information processing. Lyrics alignment is generally achieved via this method referred as forced alignment in automatic speech recognition research in the literature, which tries to find an optimal path over a sequence of phoneme posterior probabilities computed over an audio signal using a pre-trained audio lyrics transcription acoustic model. The state-of-the-art in lyrics alignment are based on the hybrid DNN HMM speech recognition framework, and specifically the CALDI ASR toolkit, and in particular the chain recipe within this toolkit that uses what is called the lattice-free maximum mutual information training scheme to train the acoustic model. Here you see a broad pipeline of achieving word timings and performing lyrics alignment using this hybrid DNN HMM framework. I'm not going to go into details of this framework, but you can find the details in the poster of this paper. There are a few challenges when trying to achieve lyrics alignment. First of all, the typical music recordings that we are dealing with have a few minutes of duration. Typically, it's like 3 to 4 minutes, but it could be more. And more importantly, there is no restriction regarding the audio length. Furthermore, there are usually long segments between vocal regions within a song. And these non-vocal segments are usually accompanied by music instruments in the background, which potentially disrupts the alignment path, causing severe errors in the alignment evaluation. Finally, the state-of-the-art in lyrics alignment uses a huge acoustic model due to the large phoneme set that they are employing. These phoneme sets are genre specific. That's why they are robust, but also it provides a huge acoustic model that can be extremely memory exhaustive. To tackle these problems to come up with a solution, we have developed this pipeline that you're seeing in the slide, and which I will be talking about its details in the next few minutes. Our goal of developing this pipeline is to be able to apply forced alignment within short audio segments so that we won't need a huge acoustic model and huge memory requirements. we apply alignment on source-separated vocals. So we won't need a huge acoustic model to handle genre-specific phonemes. For that reason, we start with vocal source separation as the initial step. Once we extracted vocals, we divide audio in smaller chunks based on an energy-based voice activity detection algorithm. But at this point, we don't know which lyrics are corresponding which of these voice activity regions. To find that, we transcribe the content within these voice activity regions. To increase the likeliness of detecting the corresponding or the desired lyrics, we build a biased decoding graph using a biased language model. We construct this language model based on the input song lyrics only, and we use a large n-gram language model to increase the context and essentially increase the likeliness of transcribing the desired word sequence. To handle out-of-vocabulary words, we generate pronunciation on the fly using a pre-trained grapheme-to-phoneme conversion tool. Once we have these, we compose the biased language model and the pronunciation models with a pre-trained acoustic model to construct a biased lyrics transcriber. Once we have these lyrics transcriber, we decode the lyrics content within these voice activity regions. When we have the transcription, we apply text alignment with the hypothesis transcription and the reference song lyrics. For selecting the anchoring words, we only consider correctly predicted words. And we select correctly predicted words or portions where there are n consecutive words matching the reference lyrics. So if we have, for instance, like 5 or n number of words that are consecutively correctly predicted, we decide that these are anchoring words. We need n words, not just a single, but n words, because there are repeating word patterns usually occurring in song lyrics. So in order to put more constraints on the order of these repeating word sequence patterns, we only consider a consecutive correctly matching words. Then based on these anchoring words and items of confidences, we again segment the whole music recording. To improve the robustness a little bit more, we restrict the output segments having at least m number of words per segment. As the next step, we apply a final pass alignment. But even to further improve the alignment results and also to explicitly denote the beginnings and the ends of each of these segments for the aligner, we add a noise tag or a noise label in between segments so that our aligner knows when to stop and when to start again. Once we have these segments and this new segmented data, we apply this traditional force alignment within these shorter segments. Now that we don't have to align the whole song, but shorter segments, our memory requirement is much lesser. And then using the same pre-trained monophonic acoustic model, we perform this alignment. Before going into empirical results, I'd like to briefly mention some of the core elements of our lyrics alignment evaluation. We have used the common evaluation metrics for lyrics alignment that have been utilized in research in the past. The first one is the average absolute error deviation. And the second one is the percentage of correct estimates according to a tolerance window of 0.3 seconds. We have evaluated our alignment system on the Jamendo lyrics dataset that consists of 20 contemporary English language songs with varying musical genre. And these songs have open source license. In this slide, on the left, the table shows the alignment results in terms of the evaluation metrics that I just mentioned. And on the right, we see the statistics on the memory usage in terms of megabytes. Note that the models that are noted as DE1 and DE2 are R methods, where DE1 applies lyrics alignment on the vocals separated by DMUX, open source Facebook source separator tool. And DE2 applies alignment on the vocals separated by splitter, which is Deezer's open source separator. According to this table, we were able to achieve similar results with the state of the art in terms of the median absolute error deviation and predicted percentage of correctly estimates. Although we have seen slightly worse results in terms of the mean of absolute error rate, we can still say that our results are comparable to the state of the art. This reduction in the mean metric is potentially due to occasionally occurring severe alignment results. We were able to achieve these results using much lower memory consumption. And quantitatively speaking, it's an order of 20 factors lower memory consumption. To gain an insight whether the audio segmentation step to able to match the correct portions of lyrics with the audio, we apply lyric transcription experiments on the resulting segments. We have observed that lyrics are recognized better on these segmented audio regions compared to the raw segments extracted via voice activity detection. With these results, we were able to achieve the state of the art on the Jamendo lyrics dataset by 15% absolute word error rate improvement compared to the previously reported best results. Note that both in lyrics alignment and transcription tasks, we have observed that the approach for source separation affects the results considerably, which should be noted down by the source separation researchers, because lyrics alignment and transcription are two of the potential applications for source separation. To sum up, we proposed a system that can perform lyrics alignment using less memory requirements on RAM that is essential for mobile applications, and it can perform the alignment regardless of the input audio length. We have observed that lyrics alignment and transcription performances are affected by the source separation method. We have reported results as good as the state of the art for both lyrics alignment and transcription. And for reproducibility, we have publicly shared the scripts to execute the proposed alignment pipeline at the following link. To see what our system achieves during inference, I'd like to share a short video demonstration with you. Thanks in advance for your attention. You can reach me anytime using this email address on the slide.
But I won't